नमस्कार बच्चों, मेरा नाम धन्या और हम लोग सीख रहे हैं ग्रेड 11 केमिस्ट्री फोर्थ लेसन chemical bonding and molecular structure. Okay, in the previous video we learned about valence bond theory and how it could not explain the geometry of the molecule. In today's video we will be learning about hybridization. What is hybridization, the concept of hybridization, and how it can explain the geometry, and also how to find the hybridization of different molecules. Okay, so first we start with what is hybridization? What is hybridization? Now, suppose if methane molecule is formed, we all saw the formation of methane molecule CH4 using the valence bond theory. And we have carbon, the central atom. Whichever atom is less in number will be the central atom. The atomic number is 6. I have 1s2, 2s2, 2p2. And taking the outer orbitals only. So this is 2s, this is 2p. I have 1 and 2. Now, here there are only 2 unpaired electrons, but methane has to form how many carbon-hydrogen bonds? In methane, carbon has to form 4 bonds, but there are only 2 unpaired electrons. For bonding, there should be unpaired electrons, right? So it needs 2 more unpaired electrons. So what would happen for carbon? This is the ground state. So in the first excited state, what would happen? 1 electron from 2s will move on to 2p. Why this is needed? Because we need 4 unpaired electrons, because there are 4 bonds being formed between carbon and hydrogen. So in the first excited state, I have 2s, I have 2p, and each having 1 electron each. So there are 4 unpaired electrons. So now carbon is ready to form bonds with the 4 hydrogen. How many hydrogens are there? 4 of them. And each hydrogen, what is the configuration? 1s1. So there are 4 of them. 1, 2, 3, 4. Second hydrogen, third hydrogen, and fourth hydrogen. Right. So what would happen? This is hydrogen and this is carbon. So how the 4 bonds are formed? 1 bond is formed between S and S. I'll take a darker color. 1 bond is formed between 1s orbital of hydrogen with 2s orbital of carbon. Another bond is formed between 1s orbital of hydrogen with p orbital of carbon. Another bond is formed between s orbital of hydrogen with p orbital of, with the next p orbital of carbon. There is another bond being formed between s orbital of the next hydrogen with the p orbital of the carbon. Now there are 4 bonds being formed. 1, 2, 3, and 4. Now all the 4 bonds are different bonds. Now all these four bonds, they are different because they are formed from different orbitals. So they should have different energies, right? But it has been seen that all the 4 bonds all these 4 bonds of methane was equivalent, was seen to be equivalent, were equivalent in all respect. That means the bond strength, the bond length were the same. Okay, so it was because these 4 bonds are made up of different orbitals. They should have been different. They should have different bond lengths, different energies, but it has been seen in reality all these 4 bonds of methane were equivalent. That means bond energy is same, bond length is same, so they were all same. Okay, so this was the failure of valence bond theory, and here is when hybridization came into play. Hybridization came into play. So here the concept of hybridization was used to explain this discrepancy, why all the bonds were having the same energy or why they were equivalent. Okay, so we see the same example of carbon. Carbon is, we use the same molecule methane. Okay, so carbon is 6 atomic number. We have 1s2, 2s2, 2p2. So here in the s orbital 2 electron, p orbital 2, and in methane, how many bonds are being formed? Carbon is forming how many bonds? 4 bonds. Here, there are only 2 unpaired electrons. So what happens in the first excited state? In the first excited state, 1 electron from 2s goes to 2p, and we get 4 unpaired electrons in carbon. Okay. Now here, this is 2s and this is 2p. Now, what is this concept of hybridization? Now, in this concept of hybridization, atomic orbitals with same energy or nearly the same energy, they intermix or mix to give new orbitals of exactly the same energy. So, what happens in hybridization? In hybridization, atomic orbitals of same or nearly same energy, what do? They intermix to give new orbitals of exactly same energy. But what is the necessary condition? That the atomic orbitals must have same or nearly same energy. Okay, then only they can intermix. For example, here 2s and 2p, they have exactly the same energy because the principal quantum number is the same, n is the same, 2s and 2p, right? So here, these 2s and 2p, they intermix. How many s orbital is there? 1. How many p orbitals are there? 3 of them. So 1, 2, 3, 4. So how many do we get? 1, 2, 3, 4. Okay, here 1s is mixing with 2 p orbitals, 2p orbitals. 1s is mixing with 2p orbitals. And sorry, 1s is mixing with 3p orbitals, sorry, 3p orbitals. So 3 plus 1, 4. 1, 2, 3, 4. So there is 1s and how many p orbitals are there? 3p orbitals, resulting in the formation of sp3 hybridization. And how many orbitals are you getting? How many orbitals are mixing? The same number of orbitals you will get. So for example, how many orbitals are mixing here? 1 plus 3. How many are there? 4. So 1, 2, 3, and 4. And each of these are sp3 hybridized. All of them are sp3 hybridized. Same hybridization. So all these orbitals have the same energy. So hybridization means is the intermixing of the atomic orbitals of same or nearly same energy to give a new set of orbitals having same energy. And the number of orbitals that mix will be the, for example, if 4 orbitals mix, you will get 4 hybrid orbitals. If 3 are mixing, you will get 3 hybrid orbitals. So how many orbitals are mixing? That much number of hybrid orbitals you will get. And what is the necessary condition? The orbitals must have same or nearly same energy. Here the mixing was between 2s and 2p. They have nearly same energy. But if I have mixing of 2s and 3p, this will not happen because the principal quantum number is different. So the energy will be different. Okay. So now here I have carbon. I have carbon. In carbon, what is the hybridization? You got 1s is mixing with 3p orbitals to give you sp3 hybridization for carbon. All the 4 hybrid orbitals are sp3 hybridized. Now, there are 4 bonds being formed with 4 hydrogen atoms. So, carbon is sp3 hybridized. And we have hydrogen, 4 hydrogen. I'll use another color. I have 4 hydrogen. Have this. 3, 4. And each of these 4 hydrogen has 1s, 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 1s1. Okay. So a bond is formed between the s orbital of hydrogen with sp3 hybrid orbitals of carbon. Another bond is formed between s orbital of hydrogen with sp3 hybrid orbital of carbon. Another bond is formed between s orbital of hydrogen with sp3 hybrid orbital of carbon. Another bond is formed, the 4th bond is formed between s orbital of hydrogen with sp3 hybrid orbital of carbon. Okay, and we get a structure like this. This is the structure of methane. And this is hydrogen. Which orbital of hydrogen is overlapping? S. This is the 2nd hydrogen with s orbital. 3rd hydrogen. For hydrogen, s orbital is overlapping. This is the 4th hydrogen. S orbital is overlapping. Okay, and the 4 orbital Now, methane attains a shape in which there is minimum repulsion. Okay, so the molecule attain an orientation in which there is minimum repulsion. So this particular shape of methane is called as tetrahedral shape. It has attained this hybridization, or it has attained this shape to have minimum repulsion. Okay, so hybridization is responsible for geometry also. So hybridization is responsible for geometry. How? Because the molecule attain the shape that so that the repulsion is quite minimum. Okay, or the orientation of the hybrid orbital is such that the repulsion is minimum. So orientation of the hybrid, so the orientation of hybrid orbital is such that there is minimum repulsion. Repulsion is minimum. Okay, and one more important point is that the hybrid orbitals that are formed, the sp3 hybrid orbitals that are formed, okay, these hybrid orbitals that are formed, all these hybrid orbitals have the character of s and p both. Okay, so if it is sp3 hybridization, it will be s character plus more of, there will be s character plus p character, both. Okay, but the p character will be more. As you can see, there are more p orbitals. Okay, so this is about hybridization. This is the summary about hybridization. Hybridization simply means it is intermixing of the atomic orbitals. What kind of atomic orbitals? Those that have same energy or nearly the same energy. They intermix to give the orbitals with exactly the same energy. How many orbitals are mixing? You will get the same number of hybridized orbitals. And these hybridized orbitals have the same energy. And they have both S and P character. I mean, it has the character of the intermixing orbitals. And the hybridization is responsible for giving geometry to the molecule. The orientation of the hybrid orbital is such that the repulsion is minimum. Okay. I hope till here it is clear. Okay. Now, coming to some main points of hybridization, some important points before we practice drawing some molecules and the geometries. Okay. First one. What is hybridization? Intermixing of orbitals, atomic orbitals of same or nearly same energy. That is very important. Nearly same energy. To give what? To give new orbitals okay, and these new orbitals will have exactly the same energy. All the new orbitals will have exactly the same energy. So orbitals of exactly same energy. Okay, And what kind of orbitals can participate in hybridization? Half-filled and half-filled and empty orbitals can participate, and empty orbitals can participate in hybridization or can undergo hybridization. Okay, fully filled orbitals cannot undergo hybridization. The third one is the number of hybrid orbitals is equal to number of intermixing orbitals. If 3 orbitals are mixing, we get 3 hybrid orbitals. If 4 of them they are mixing, we get 4 hybrid orbitals. Then, this concept of hybrid orbitals is for, the concept is for only what kind of bonding? Concept of hybrid orbitals or hybridization is for sigma bonds, that means single bond, and also for lone pair of electrons, but not for pi bonds, not for pi bonds. Okay. Then hybrid orbitals, how are they named? So hybrid orbitals are named from the parents, or the parent orbitals are named from the parent orbital. For example, if one s orbital is mixing with one p, we get, so one s is mixing with one p, we get, because 2 of them they are mixing, we get 2 orbital, each of them they are sp hybridized. 2 are mixing, 2 orbitals are mixing to give 2 hybrid orbitals. Okay, if 1s and 2p, so 1s and 2p are mixing, we get 3 hybrid orbitals. All of them, they are sp2, sp2, sp2. Similarly, if I have 1s and 3p mixing together, so 1s and how many p orbitals are mixing? 3 of them. I get 4 hybrid orbitals, 1, 2, 3, 4. All of them, they are sp3 hybridized with equal energy also. Then, if I have 1s is mixing with 3p and 1d. So 1s, 3p, and 1d. I will get how many? 1, 2, 3, 4, 5. 5 hybrid orbitals. 1, 2, 3, 4, 5. Each of them sp3d, 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 1, 2, 3, 4, sp3d. 5 of them. Okay. So again, if I have 1s, 3p, and 2d, if they are combining 1s, 3p, and 2d, if they are combining together, you get 6 hybrid orbitals. 1, 2, 3, 4, 5, 6. Each of them sp3d2. Okay. So the number of hybrid orbitals combining is equal to the number of hybrid orbitals we get. Okay. And they are named after their parent orbitals. Okay. So I hope it is clear. And what kind of hybrid orbitals they undergo hybridization? Half-filled or empty orbitals. Okay. And concept of hybridization is for sigma bonds, not for pi bonds. Okay, moving on further. Shape of hybrid orbital. Seventh one. Okay. Now, these hybrid orbitals, they have a common shape. Okay. Like, for example, if we know that the s orbital spherically symmetrical, this is the p orbital with 2 lobes, d orbitals with 4 lobes, right? So these are just the orbitals. Okay. Now, here, if suppose these are just the shapes of the orbitals. S is spherically symmetrical, P has 2 lobes, D has 4 lobes. All these we have learned. Now, how do we know that the hybridization has taken place or not? Okay, if a hybridization has taken place, it will be shown with a big lobe and a small lobe, like this. If you see a very big lobe like this and a very small lobe like this shows that hybridization has occurred. Hybridization has occurred. Okay. Sometimes they show it like this also. Like, okay. And so in this picture also, you can see there's a big lobe and a very small lobe. Sometimes in some books, these small lobes are missing also. Sometimes they just show like this. So when you see these big lobes, you can understand that what has taken place, hybridization has occurred. Okay, so this is the shape of the hybrid orbitals. They show it with a big lobe, and sometimes along with the big lobe, there will be a small lobe like this. Okay, sometimes the small lobes are missing too. Okay, moving on further, the orientation of the hybrid orbitals. Orientation of hybrid orbitals is such that there is minimum repulsion. There is minimum repulsion. Okay, and this creates a geometry. So this is responsible for the geometry of the hybridized orbitals and provides stability to the orbitals. Okay, so orientation of the hybrid orbitals is such that there is minimum repulsion. Now, the type of hybridization. So these are the main points, students. Okay, we will be discussing about some shapes of the hybrid orbitals now. Now, before we move on, we'll come to types of hybridization. That tells you about the geometry of the orbitals. And also we will discuss some examples. Okay. Now, the first one is 1s and 1p. When 1s and 1p mix together, we will get 2 hybrid orbitals, each with sp hybridization. Okay, 1s and 1p, sp hybridization, and the shape is linear. Okay, the shape is linear. As you can see, I've not shown the smaller loop. I'm just showing it like this. And the bond angle is 180 degree. So For sp hybridization, what is the orientation? It is linear. Okay, I hope it is clear. So whenever you come across sp hybridization, what should come in your mind? Linear. And what is the bond angle? 180 degree. For example, BEF2. BEF2. So beryllium is bonded to fluorine atom. Okay, it can be like this. It can be like this too. How do we confirm what is the shape or what kind of bonding is happening? Okay, for that, let's check out beryllium. It is atomic number is 4. So 1s2, 2s2, okay, and fluorine is 9, 1s2, 2s2, 2p, 5. Okay, now fluorine, here I have 1, 2, 3, 4, 5. Okay, now here, beryllium, if you see, I'll just show the 2s. Beryllium needs to form 2 bonds with 2 fluorine atom, but it has s orbital, it is fully filled. I need to get some unpaired electrons. So what comes into play? That p orbital come into play. And in the excited state, 1 electron goes from s to p. And what do we get? We get 2s, 2s, and in the 2s, I have 1 electron, and I have 1 electron in 2p orbital. Now, what happens is that this S and P, they intermix to give you sp hybridization, resulting in the formation of 2 hybrid orbitals. Okay, and each having an unpaired electron, and that will form a bond with the 2 fluorine atom, with the p orbital of the fluorine atom. This is the second fluorine atom, this is the first fluorine, and this is the second fluorine. With which orbital of fluorine? With the p orbital of fluorine. So it is p-sp bonding. P-sp bonding. And both these bonds are seen to have same energy. Okay, and what is the geometry of beryllium fluoride? It is linear, and the bond angle is seen to be 180 degree. Okay, bond angle is seen to be, geometry is seen to be linear. Okay, so there is intermixing. I hope till here it is clear. Okay, now this is the first one. Second one is, so I hope this is clear. So you must remember that whenever we come across beryllium fluoride, it has the linear geometry with bond angle of how much? 180 degree. This is the first example. Now coming to the second example or second type of hybridization, if 1s and 2p are mixing together, okay? If 1s is mixing with 2p, we get 3 hybrid orbitals. Each of them is sp2 hybridized. Okay, and what is the shape? The shape is triangular planar. And what is the bond angle? It is 120 degree. 120 degree. What is the name of the shape? Triangular planar. Plane, sorry, triangular plane. Triangular plane. Okay. Okay. So sp2 hybridization, and it is triangular planar. Triangular planar. And what is the bond angle? Bond angle is 120 degree. Triangular planar. So an example is BF3, boron trifluoride. Now boron has an atomic number of 5. So the configuration is 1s2, 2s2, 2p1. Fluorine, the atomic number is 9. I have 1s2, 2s2, 2p5. So this is the 2p orbital of fluorine. So 1, 2, 3, 4, and 5. Okay, so this is the first fluorine, and this is the second one. Sorry, I drew extra orbitals for F. 1, 2, 3, 4, 5. Second fluorine. One more is there. 1, 2, 3, 4, 5. This is the third fluorine. Right. Now, for boron, this is 2s. This is 2p, 1 electron. Okay. Now, boron has to form 3 bonds. So it needs 3 unpaired electron. So what happens? S and P, they intermix. But before intermixing, we need the unpaired electron. Yes, I was about to make a mistake to intermix the fully filled orbital, which does not take place. I cannot intermix a fully filled orbital. So what does it do? It undergoes excitation, and the electron will get transferred from 2s to 2p. And I have first excited state. Okay, so I have 1s, 1 electron, and in 2p I have 2 electron now. Now they are in the position to intermix because all these have unpaired electron. Remember when we were discussing the main points, we said the orbitals must be half filled or empty for intermixing. So we have the requirement of 3 orbitals. So they will intermix, and I will get 3 orbitals. Each of them, there is one s is mixing with 2p orbitals, right? So I have sp2, sp2, sp2. One s is mixing with 2p orbitals. So sp2, 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 each of them have unpaired electron. Now this sp2 hybridized boron atom, boron is ready to form bonds with the 3 fluorine atom. And what kind of bonding it is? p-sp2 bonding. The p orbitals of fluorine is mixing with sp2 hybridized orbitals of boron. Okay, and it has a shape of triangular planar. Triangular planar. Fluorine, fluorine, fluorine. What is the bond angle? The bond angle is 120 degree. Okay, so the bond angle is 120 degree. So this was about sp2 hybridization. Okay. And remember that hybridization occurs only for those orbitals that are half filled, not fully filled. Okay. Or empty also, that also is no problem. Now, the third type of hybridization that takes place is, suppose 1s is combining with 3p orbitals. Okay, 3p orbitals, we get sp3 hybridization. And how many orbitals we get? 4 of them. sp3, 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 and sp3. Okay, so let's check out an example. And for example, shape is, yeah, the shape is tetrahedral. The shape is tetrahedral. So I have like this. And the bond angle is 109.5 degree. Okay. Example, methane. Okay. Now carbon atomic number is 6. Carbon 6. Okay. 1s2, 2s2, 2p2. Okay. So this is 2s orbital. This is the 2p orbital. 1, 2. Okay. Now carbon has to form how many bonds? 4 bonds, right? 4 bonds it has to form. There are only 2 unpaired electrons. So what can happen? It cannot form undergo hybridization now like this. It has to have unpaired electrons, right? And it needs 4 hybrid orbitals. So 1 electron gets transferred from 2s. This is the 2s and this is 2p. And what do we get? In 2s, we have 1 electron. 2p, I have 1 electron each in all these orbitals. Okay. Now carbon is now ready. This is the first excited state. Carbon is now ready. Orbitals are ready to undergo hybridization because I need 4 hybrid orbitals and all these 5 hybrid orbitals are half filled, right? So they will intermix and I get how many hybrid orbitals? 1, 2, 3, 4. sp3, 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 sp3. 4 hybrid orbitals. Okay, and each having 1 electron each. And each of these sp3 hybrid orbitals will form bonds with s orbital of hydrogen. Okay, and we'll get what shape? Tetrahedral with a bond angle of 109.5 degree. 109.5 degree. So I hope it is clear. Moving on further, this is the third type of hybridization, right? The fourth type, 1s is combining with 3p and 1d. How many orbitals do we get? 1, 2, 3, 4, 5. We get 5 orbital, 1, 2, 3, 4, 5, sp3d. Each of them sp3d. Okay. For now, just understand what's happening, and at the end, but the shapes you have to memorize. Okay, you have to memorize the shape. Okay. So the shape is, so this is sp3d, and the shape is trigonal. So this is trigonal, bipyramidal. So one is above and one is below. Okay, so this is the trigonal shape. They are in the same plane. This has a bond angle of how much? 120 degree. Now, bipyramidal, trigonal, bipyramidal. So, I have two of them. This is one above the plane and one below the plane. So, that is 90 degree. 90 degree. So, this is trigonal bipyramidal. 90 degree. So this is trigonal bipyramidal. 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 Bye. bipyramidal. Okay, so those that are in the same plane, it is 120 degree, one above and one below the plane, that is 90 degree. Example is PCl5. Okay, I hope it is clear. Now the ones that I have drawn with blue, this one, it is in the same plane. The one that I have drawn with red, it is one below and one above the plane. Okay. I hope till here it is clear. Okay. Now, moving on further, the fifth one, the shape, there is no other choice. You have to memorize the shape of each type of hybridization. Okay. So suppose if I say sp3, it is tetrahedral, you must remember. Okay. If it is sp2, trigonal, triangular, planar, you have to remember that. Now, if I have one S is mixing with 3P and 2D, D and D. What do I get? sp3d2. There are 6 orbitals, right? 6 hybrid orbitals, right? So it has a shape 1, 2. It is octahedral. Octahedral. Because it has 8 faces. Octahedral. Okay. So example is SF6. Okay. So if the hybridization sp3d2, what is the shape? Octahedral. Okay. Example is SF6. Okay. Now, the next one is if 1s is mixing with 3p and 3d, it results in sp3d3. How many orbitals are they? 3, 3, 6, 7 orbitals. 7 hybrid orbitals we get. Okay. And we get pentagonal. This is pentagonal. Pentagon, right? Pentagonal bipyramidal. So pentagonal bipyramidal. So okay, so pentagonal bipyramidal is the shape. Okay, so the geometries of each type of hybridization you have to learn. Okay, so for example, we started with sp hybridization. If it is sp, you have to learn that it is what? It is linear. The geometry is linear. If it is sp2, you have to learn that it is triangular planar, right? If it is sp3, you have to learn that it is tetrahedral, bond angle, wherever mentioned. Fourth one, if it is sp3d, 5 hybrid orbitals, trigonal bipyramidal. Fifth one, if it is sp3d2, it is octahedral. Sixth one, if it is sp3d3, pentagonal bipyramidal. Okay, so pentagonal means 5 sides and bipyramidal means one is above and one is below the plane. Okay, so one is above. So 1, 2, 3, 4, 5, and one above and one below the plane. Okay, so that makes it 7 hybrid orbitals. So I hope it is clear till here. Pentagonal bipyramidal, right? Now, students, let's check out how to find the hybridization, okay? Because it is not possible to memorize so many structures. So what is the way to find the hybridization? So our next topic is to find hybridization. Because practically it is impossible to memorize all the structures. So there are two ways to find the hybridization. One way, if the structure is given to you, you know the structure, or at least you know how many single bonds are there, or how many lone pair of electrons are there. Okay, if this is known, okay, we can find out the hybridization. If we know the hybridization, you will know the shape. That you have to know it, okay? Then the other way is knowing the formula. Okay, let's go one by one. This is the first way. This is the second method. Okay, so the first one, by knowing the structure. By knowing the structure, how do you know the hybridization? Okay, first is we calculate something called Z. By calculating, so this is the first one where we are doing, calculate Z. And what is Z? It is the sum of number of sigma bonds plus lone pair of electrons in the central atom, on central atom. So here I told you, if you know how many single bonds are there or how many lone pairs are there, we can calculate what, or we can understand the hybridization. Okay, if the structure is given, then also we can understand the hybridization. Okay, so calculating Z. Z is the sum of sigma bonds plus lone pair of electrons. So if Z is 1 or Z is 2, okay, Z is 2. Z cannot be 1, right? Because it is the combination of 2 or more orbitals. If Z is 2, the hybridization is sp. Okay. If Z comes out to be 3, that means 3 orbitals have mixed up and we get sp2. sp2 is itself is 3 hybrid orbitals, right? If Z value is 4, it means we get 4 hybrid orbitals. So sp3, definitely it will be sp3. Then if Z is 5, definitely 5 orbitals have been formed, or 5 hybrid orbitals are being formed. So sp3d. If the Z value is 6, that means 6 hybrid orbitals are being formed. So definitely it is sp3d2. Okay, so this sp means 2 hybrid orbitals. sp2 means 3 hybrid orbitals. That you know already. Okay, now let's check out with an example. Suppose I have SO3, sulfur trioxide. Okay, so suppose you know the structure. The structure is given to you. The structure is given, suppose. Okay, so if the structure is given, you know you can see that there are three double bonds. Sorry. So if it's a double bond, one is a sigma bond, one is a pi bond. We don't need the pi bond here. There's a sigma bond here. There's a sigma bond here. So let's calculate. S is the central atom. Let's calculate Z. Z is, what is the formula of Z? Is the number of sigma bonds plus lone pair of electrons. So I don't have a lone pair here. I have 3 sigma bonds. If Z value is 3, what kind of hybridization? sp2. If it is sp2, what is the geometry? Triangular planar. Triangular planar. Okay, so this, by calculating the Z value, you can get the hybridization. Once you know the hybridization, you know the geometry for each of these hybridization. You know the geometry, you must know it, you must memorize it. No other way. Okay. Coming to the second one is water. Suppose this geometry of water is given to you. There's a lone pair here. There's a lone pair here. Okay. So let's calculate Z. This is 1 sigma bond. There's 2 sigma bond. 2 sigma bonds plus. How many lone pairs are there? Lone pair. They are not asking the number of electrons. The lone pair. They are asking pair. How many pairs are there? This is 1 pair. This is 2 pairs. So 2 lone pair. So it is 4. Right. So 4 means it is 4 hybrid orbitals. It is sp3. And what is the geometry? Tetrahedral geometry. This is the second example. The third one is ammonia. Suppose the shape is given to you. There is one lone pair of electron. One lone pair will have 2 electrons, but the formula is 1 lone pair, the lone pair of electrons. There are 3 hydrogen atoms. And what is the sigma bond? How many are there? 3 of them. So what is the Z value? Z value is number of sigma bonds plus 1 lone pair. So that gives you 4 lone pair. Right. So the shape is what? The shape is tetrahedral. Okay. And the geometry is tetrahedral. Okay. Now, next one is sulfate ion. Okay. So this is possible only when the structure is given to you. Okay. Or you know the structure. Or at least you know how many sigma and pi, not pi bonds, how many sigma bond or lone pair of electrons are there. Please remember, pi bonds we don't consider here. Okay. So, okay. So lone pair is 0. There's a sigma bond here. 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 So Z is equal to 4 sigma bonds plus 0 lone pair. So 4 means sp3. What is the geometry? Tetrahedral. Coming to the fifth one, PCl5. Okay. Suppose they give you the structure for porous. Chlorine should come here. Okay. So there's no lone pair. Z is equal to how many sigma bonds are there? 1, 2, 3, 4, 5. 5 sigma bonds are there. All right. So 5 hybrid orbitals. So sp3d. So trigonal bipyramidal. So trigonal bipyramidal. So trigonal bipyramidal means 3 of them, they are in the same plane. This is the shape, structure, right? So 1 above the plane and 1 below the plane. This is the structure, trigonal bipyramidal. Okay. I hope it is clear. So this is not the structure. This is only for knowing how many sigma bonds are there. Okay. Moving on further. Suppose I need to find the type of hybridization in nitrogen in nitrate ion. Now, suppose I have been given a structure like this. At least I know how many double bonds or how many lone pairs are there, if there is any. Oxygen, oxygen. Okay. So here there's a sigma bond. Here there's a sigma bond, there is a sigma bond here. So lone pair, how many lone pair is there? 0. So Z is equal to how many sigma bonds? 3 sigma bonds. So Z is equal to 3 means 3 hybrid orbitals. That means it is sp2. So triangular planar. Okay. Then I have phosphorus in phosphate ion. Okay. Suppose this is the structure, suppose. Okay. And from this structure, we can understand that there are 4 sigma bonds and there is no lone pair. Lone pair is 0. So Z is equal to 4 sigma bonds plus lone pair is 0. So it is 4. 4 means 4 hybrid orbitals, which is sp3. And what is the geometry? Tetrahedral. Okay. Suppose if a question is asked, suppose find the hybridization of all the carbon atoms. Suppose I give the structure like this. Suppose carbon is connected to carbon, is connected to carbon. Okay, so 1, 2, 3, 4. Here there will be 3 hydrogen atoms. Here this 1 hydrogen and here no hydrogen because the carbon valency is satisfied. Okay, so I number the carbon atom number 1, carbon atom number 2, carbon atom number 3. Okay, so here you just have to find the hybridization. Now, carbon atom number 1, what is the Z value? But before that, let's write the sigma bonds. This is 1 sigma bond, another one, sigma, 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 and sigma. Carbon atom number 1, how many sigma bonds are there? 4 of them. So if Z value is 4, it is sp3 hybridization. Okay. For carbon atom, this is for carbon atom 1. Carbon atom 2, Z value, how many sigma bonds are there? 2. So if it is 2, it is sp hybridization. Okay. For carbon atom number 3, for carbon atom 3 also, I have 2 sigma bond. So there's no lone pair. So Z value is 2. That is also sp hybridization. Okay, so this is how you find out if this kind of a question is given. Okay, now, so I hope if the structure is given or if you know how many single bonds and how many lone pairs are there, you can understand the geometry and the hybridization. Now let's understand how to tell about the hybridization if you don't know the structure, but if you know the formula. Okay, so this is the second method. Okay, now so the trick is Z is equal to half of number of, this is when you know the formula. Okay, what is the trick to understand the hybridization? We find out the value of Z, where Z is equal to half of number of valence electron on central atom plus any negative charge minus any positive charge plus number of monovalent atom. Monovalent atom refers to anyone having a valency of 1, hydrogen, chlorine, bromine, iodine, okay, fluorine. All these are monovalent atoms. Okay, so if we know Z, we will understand the hybridization. Okay, because we already know the table over here. I already gave you the table here. Here, if you know Z, you will know the hybridization. Okay, but this formula we are using if we don't know the structure. The formula that I just gave you now, this formula we use when you don't know the structure. Okay, or how many sigma bonds or how many lone pairs are there, we can use this formula. For example, ammonia. Now, nitrogen is the central atom. Atoms less in number is the central atom, right? So Z is equal to half of number of valence electron on the central atom. Nitrogen is 5, right? So 5, valence electron is 5, plus. There is no positive, there is no negative charge. Number of monovalent atom is hydrogen. How many hydrogens are there? 3 of them. So half times 8, which is equal to 4. If Z is equal to 4, it is sp3 hybridization, 4 hybrid orbitals. Okay, moving on to water. Okay, Z is equal to half of. Central atom is oxygen, less in number. The valence electron, 6, plus. There is no positive charge, no negative charge, plus. There is monovalent atom, that means hydrogen. How many are there? 2. So 8 by 2, which is equal to 4. It is also sp3 hybridization. Now, carbon in carbonate ion. Okay, Z is equal to half of. Carbon is what? Central atom, 2, 4. 4 is the number of valence electron, plus. We need to add the negative charge. 2. There is no monovalent atom. There's no positive charge. 6 by 2, which is equal to 3, which is sp2 hybridization, which is triangular planar. Okay. Then again, nitrogen in NO3 minus. Okay. So I have half of nitrogen is 2, 5, 5 valence electron, plus there's a negative charge, I add them, there's no monovalent atom. So 6 by 2, which is equal to 3, which is sp2 hybridization. Okay, now you have to find the hybridization of these given structures. So find the hybridization. Okay, silicon in SiF4. Okay, silicon is the valence electron is 4. Okay, it's the carbon family. So 4, so half of 4 plus, there is no positive or negative charge, but monovalent. Fluorine is a monovalent. How many are there? 4. So 8 by 2, which is equal to 4. 4 means sp3, that is tetrahedral. Second one is sulfur in SF4. Half of, what is the valence electron? Sulfur is the oxygen family. So 6 plus. There's no positive, there's no negative, but monovalent is there, 4. So 10 by 2, which is equal to 5. 5 hybrid orbitals, sp3d, trigonal bipyramidal. Then I have sulfur in H2S. Half of sulfur is oxygen family, so 6 valence electron plus no most positive, no negative, but there's a monovalent atom, hydrogen. So 8 by 2, which is equal to 4. So sp3. Okay, tetrahedral. Fourth one, xenon in xenon oxyfluoride. Suppose I need to find the hybridization. Half of, the formula is half of number of valence electron. How many valence electrons? Xenon is from the noble gas family, so valence electron will be 8. Okay, there's no positive charge, so no negative charge, but there's a monovalent atom, fluorine. How many are there? 2. So 8 plus 2, 10 by 2, which is equal to 5, sp3d. So if sp3d is the hybridization, because there are 5 hybrid orbitals. Right. Fifth one is xenon in XeF4. Half of number of valence electron in xenon. Xenon is the noble gas, 8. So noble gases have 8 electrons in the outermost shell. There's no negative, no positive charge, but there's a monovalent atom, fluorine. How many are there? 4 in number. So 12 by 2, which is equal to 6, which is sp3d2 octahedral. Then one more is there, sixth one, sulfur in SO3 2 minus. Half of sulfur is oxygen family, so 6 valence electron plus. I have to add the negative charge 2. There's no positive charge, there's no monovalent atom. So 8 by 2, which is equal to 4, which is sp3 tetrahedral. Okay, so even if you don't know the structure, you can still find out the hybridization. Once you know the hybridization, you have to know the shape. Okay, so this is the formula. I hope this is clear, right? Okay, students. So today we learned about the hybridization, what is the hybridization and how the orbitals undergo hybridization, and also to find out the hybridization, if the structure is known. If the structure is not known, also we can find out by knowing the formula. Okay, so that's all for today, students. Thank you. Have a great day.